In this section, we will explore how the system operator maintains the operational reliability of the system using ancillary services provided by market participants. All the participants in electricity markets rely on the power system infrastructure. And all of them, but especially consumers, have expectations regarding the reliability of service. Nobody wants to be left out in the dark. And maintaining this continuity of the service is a responsibility of the system operator. But to be able to do this, it needs the market participants, particularly the generators, to provide services. But first, let's clarify what we mean by operational reliability. First, the system must be able to operate continuously if the situation does not change. Second, the system must remain stable even in the event of common contingencies, such as the occurrence of a fault on a transmission line or failure of another component, sudden failure of a generating unit, or a rapid unanticipated change in load. Now, the operator must consider the consequences of these contingencies and take actions, and it's going to use both preventive actions and corrective actions to deal with these contingencies. The idea of preventive action is that the operator should put the system in a state such that it will remain stable even if a contingency occurs. Now, taking these preventive actions means operating the system at less than full capacity, keeping some security margin. But doing that will limit the commercial transactions that this system operator will allow. On the other hand, corrective actions are taken only if a disturbance or contingency does occur, and their purpose is to limit the consequences of this disturbance. But to be able to put in place those corrective actions, the system operator is going to need resources that belong to market participants, particularly generators. And these resources are called services, and they will have to be purchased from the market participants by the system operator because, well, they're providing a service and they should be paid for it. Now, when called upon, some of these ancillary services will deliver some energy. But what really matters is not so much the energy that they will deliver, but the capacity to deliver this energy if a contingency does occur. So it is better to remunerate those services on the basis of availability rather than on the provision of energy when they are called. So here's the outline for this section. We'll start by describing the needs for ancillary services, and that will involve both keeping the generation and load in balance, and second, maintain the operational reliability of the transmission network. Then we will talk about obtaining ancillary services. How much ancillary services should the system operator buy, and how should it go about obtaining those services, and who should pay for these services. And finally, we will take the perspective of the people providing ancillary services and see how they can maximize the profits that they get from the sale of energy and ancillary services. But let's start by discussing the needs for ancillary services. The first thing that the system operator must do is balancing production and consumption. And to study that, we are going to assume that all the generators, loads, and tie lines are connected to the same bus. So we are not going to consider transmission network yet. In this case, the only variables that we have to consider are total generation, total load, and net interchange with other systems. If the production and consumption of electrical energy are equal, the frequency of the system will remain constant. However, in practice, we have constant fluctuations in the load, the generators are not controlled with complete accuracy and don't always produce exactly what they are supposed to produce, and we have sudden outages of generators and interconnectors with other systems. If we have more load than generation, the frequency will drop, and on the other hand, if we have more generation than load, we will have an increase in frequency. Now, generators can only operate within a narrow range of frequency. That's why the system operator needs to keep the frequency close to the nominal value of 60 Hz or 50 Hz. If it doesn't keep the frequency within this narrow range, the protection system of the generators will disconnect these generators when the frequency is too high, and this will cause further imbalances between load and generation. So that's why the system operator must maintain the frequency within these limits. The rate of change in frequency is inversely proportional to the total inertia of the generators and the rotating load. Therefore, the frequency is going to change much less in large interconnected systems like the Western interconnection, the Eastern interconnection, or the European transmission system it does in small isolated systems like you would find in small islands. On the other hand, local imbalances in an interconnected system was going to cause undesirable changes in the tie line flows. So for example, if a generator fails in the green area shown in this diagram, it will cause an increase in the flow from the red area to the green area. This inadvertent flow is considered totally undesirable and needs to be compensated. These inadvertent flows must be dealt with quickly because they can overload the tie lines, and the protection system might then therefore decide to disconnect these lines, which could lead to further imbalances between load and generation in the two areas. Therefore, it is important for each system, even in a large interconnection, to remain in balance. Now, minor frequency deviations and minor inadvertent flows are not an immediate threat. However, they weaken the system, and therefore they must be corrected quickly so the system can withstand further problems. Let's take an example to see how all this might work. Let's consider how the load fluctuates over 5 trading periods. So in this diagram, we see how the load fluctuates over these 5 periods, and you can see that we have a general trend, but we also have some random fluctuations. Electricity markets tend to operate over fixed periods, and consider the load is fixed over these periods. So the energy traded for each period would tend to be given and fixed. Now, there is often a difference between the energy traded and the energy actually produced. This difference consists of small differences in the middle of periods, and then some deviations at transition between periods. And there are also, as in the middle of period 4, cases where there's a sudden outage that creates a major imbalance between load and generation. So, instead of plotting the load and the energy produced and the energy traded, let's consider just the imbalances, which are the difference between the load and the energy produced. So this diagram showed these imbalance for these 5 periods. And we can observe several different things. We have in blue random load and fluctuations. In red we have the slower load fluctuations due to the change between periods and being the fact that the load is increasing. And then in the middle of period 4 we have a large outage that creates a large negative imbalance. Let's summarize what we have observed in this example. We have differences between load and energy traded because the energy traded does not track the rapid load fluctuation, because the market assumes the load is constant over a trading period, and also because we have errors in the forecast. We also have differences between the energy traded and the energy produced because of minor errors in the control of the generating plant, because of the fact that the generating plant have a finite ramp rate and cannot, instantaneously change from the level where they're supposed to be at the end of one period and the beginning of the next. And then we have imbalances created by or caused by unit outages. Now, to deal with all these imbalances, we're going to need balancing services. But as we showed in the previous example, we have different phenomena due to these imbalances, and each of these phenomena has a different time signature. We're therefore going to require different services to handle these phenomena. And unfortunately, the exact definition of these services is going to differ from market to market. So when you are comparing services from different markets, you have to make sure that you are always talking about the same thing. Service needs a ratio design has inflation low and all intermediates in ratio. Now, if this remain phenomenal, interchanges are valid. Serve and be by the general unit because they're quick, they connect grid, they equip a generator, until they do AD auto generation code. Next is following serve and up here load flushes lower and design sure the frequencies common and interchange may add the right for natural use. This service also provides getting type spawn agent. Reserves and predecessors by generators. Two types of reserve would be to start it would not available. We would have supplemental that would slowly may not be nice and is reserved to sure available with now the demonstration and the market you are discussing. So therefore to ensure the names that you use which you intend to say. Let's move on to network issues or how the operator makes sure that the operational reliability of the transmission network is maintained. And these operators will continuously perform contingency analysis. And that means that they will check that no credible contingency would destabilize the system based on the current operating conditions. Now, the system can be destabilized in different ways. There could be thermal overloads that might cascade from line to line. We can have transient instability or angular instability, and we can have voltage instability. And if the operator detects that one of these contingencies could destabilize the system, it is expected to take some preventive action to make sure that that does not happen. So what types of preventive actions can an operator take? Well, there are essentially two main types. You could say the first type is the low-cost preventive actions, and that includes adjusting the taps of transformers, adjusting the reference voltage of the generators, adjusting the phase shifter taps. All of those have a low cost or essentially a zero cost. They can be effective, but it can be somewhat limited what can be achieved with these low-cost preventive actions. There are also higher-cost preventive actions, which typically involve restricting the flow on some branches, and that is achieved by requiring some generators to limit their outputs. But in the electricity market, that means it's going to affect the ability of some of the producers to trade on this market. Let's consider a small example to explore how the thermal capacity of lines limits the ability to trade and how this can be dealt with using ancillary services. In this small system we have two buses and a generator connected at A and a generator connected at B, but most of the load is connected to B. Now let's assume that each of the lines between A and B is rated at 200 megawatts. In this system, the generator at A can only sell 200 megawatt to the load at B, because the 200 megawatt remaining of transmission capacity must be kept in reserve in case of outage of one of these lines. But let's consider a variant on this example. Again, let's assume that each line has a rating of 200 megawatts. If I can overload each line by 10% because it has an emergency rating of 20 minutes, then if generator B can increase its output by 20 megawatts in 20 minutes, generator A can sell 220 megawatts to the load at B. So the services provided by this generator at B helps the operation of the market because it makes it possible for A to serve the load. Let's now use a small example to explore how transient stability limits what can be done in electricity markets. Let's take again this small example and let's make a few more assumptions. Let's suppose that the bus B can be considered to be an infinite bus, that the transient reactor of generator A is 0.9 per unit, and that this generator has an inertia constant h of 2 seconds. Let's suppose that each of the line has a reactance of 0.3 per unit, and that the voltages are at nominal value. And let's assume that there is a probability of a fault on one of the lines between A and B, but if such a fault were to occur, it would be cleared in 100 milliseconds by tripping the affected line. Now, if we put all this data in a transmissibility program, we find out that the maximum power that can be transferred from A to B that would not cause the whole system to become unstable is 108 megawatts. So if we allow A to sell more than 108 megawatts to the load at B, we risk an instability in case of a fault on one of the lines. Voltage and voltage stability considerations can also limit the amount of power that can be traded. So let's go back to our example, and let's suppose that we don't have any reactive support at B. Well, in this case, if we use a load flow program, we can calculate that 188 megawatts can be transferred from A to B or sold by A to the load at B before the voltage at B drops below the standard limit of 0.95 per unit. So definitely we would not want to allow A to sell more than 198 megawatts to this load. However, if we assume that we can have a fault on one of these lines, and we will get a voltage collapse in the system if the power transfer from A to B is larger than 166 megawatts. So in this case, this voltage stability problem is more severe than the normal voltage limit problem, and the power that can be sold by A to B should be limited to 166 megawatts. However, if we have 25 megavar of reactive support at B, then calculations show that we can allow A to sell 190 megawatts to the load connected to bus B before an outage of a line would cause a voltage collapse. This last example shows that reactive power resources can be used to maximize the active power that can be transferred to the transmission network. Now, some of these resources are typically under the control of the system operator. For example, the system operator can control mechanically switched capacitors and reactors, can put the set points on static VAR compensators, and is responsible for setting the transformer taps. However, the best reactive power resources are the generators. Those are the ones that are really going to prevent voltage collapse. So it's necessary to define some voltage control services that will help the operator maximize the transmission capacity in the system. But that means we need to define under what conditions these resources can be used by the system operator. And when we specify these voltage control and reactive support services, we must consider both the normal and abnormal conditions. By normal conditions, I mean, for example, keeping the voltage at all buses between 0.95 per unit and 0.05 per unit. And by abnormal conditions, I mean providing enough reactive power to prevent a voltage collapse in the event of an outage of a line. Typically, the requirements for abnormal conditions are much more severe than the requirements for the normal conditions. And in a sense, you can say that reactive support is more important than voltage control. If you can do reactive support, usually you can do voltage control. Let's go back to a simple example to see how voltage control services might work. We'll use a slightly more detailed model of the lines that includes the resistance, the reactance, and the shunt susceptance of each line. We'll assume that the load at B has unity power factor and that the voltage at A is maintained at nominal value by the generator connected to that bus. And we would like to control the voltage at B, and we will use reactive power produced by generator at B or some kind of reactive compensator at B. And we will do that as a function of the power being transferred from the generator at A to the load at B. And the results are shown on this slide. These results are obtained by running a power flow calculations for various values of the power transferred from A to B. On the vertical axis on the left, we have the reactive power injected at B, and on the right, we have the voltage at B. Now we can see that for low value of the active power transfer from A to B, the Ferranti effect, due to the susceptance of the shunt susceptance of the lines, makes the voltage at B to be high. Therefore, to keep the voltage at B at or below 1.05 per unit for values of the active power transfer less than 100 megawatts, the generator at B or the reactive power injection at B has to be negative. Between about 100 megawatts and 140 megawatts of power transfer from A to B, the voltage at B is naturally between 1.05 per unit and 0.95 per unit. Once the power transfer exceeds 140 megawatts, then we have to inject positive reactive power at B to keep the voltage at B at 0.95 per unit. Now we can use this example also to explore whether we could control the voltage at B using the generator connected to bus A. And here are the results. But we will find that there are some severe limitations. For example, if we try to maintain the voltages at both buses between 0.95 and 1.05 per unit, we can only transfer no less than 49 megawatts and no more than 172.5 megawatts from A to B. If we transfer 49 megawatts from A to B, the voltage at B is at its maximum value of 1.05, while the voltage at A is at its lowest value of 0.95. If we try to transfer any less than 49 megawatts, well, these voltages would exceed the upper limit at B and the lower limit at A. On the other hand, if we try to transfer more than 102.5 megawatts, the voltage at B would be below 0.95 and the voltage at A would be above 1.05. So the conclusion is that local voltage control is much more effective than remote voltage control. That means that if we pay generators for providing voltage control, they pretty much have market power at the buses where they are located, because they're best placed ones to provide reactive support. As I have mentioned before, these voltage control or reactive support services are used not only for normal conditions but also for post-contingency conditions. And we can use our same example to study these conditions. So in this example, we are looking at how much reactive power is to be provided at B to prevent a voltage collapse in the event of a line outage between A and B. And this amount of reactive power that needs to be provided at B is calculated as a function of the power, the active power, being transferred between A and B. And the figure below shows that if this power transfer is less than 85 megawatts, we're okay. We don't need any post-contingency VARs being provided at B. On the other hand, if we transfer more than 85 megawatts, well, we need to provide reactive support post-contingency at B to avoid this voltage collapse, and the amount of reactive support that needs to be provided at B increases rapidly with the power being transferred from A to B. So the system operator should have some kind of agreement with the generator at B to make sure that it is capable of providing the megavars needed to prevent a voltage collapse. It is interesting to consider this example in a bit more detail. Let's first look at the pre-contingency conditions. The pre-contingency conditions, both lines are in service, and generator at A is generating 136 megawatts and absorbing 26 megavar to keep the voltage at A at 1 per unit. The load at B is consuming 100 megawatts at unity power factor, therefore there are 0 megavar of load. The generator at B is not producing any megawatts, but is producing 1.2 megavar to keep the voltage at B at 1 per unit. The load, the both active and reactive loads, are equally divided between the two lines, with the active load flowing from A to B, and we have 3 megawatts of losses in each line. And under these relatively lightly loaded conditions, the shunt susceptance of the lines make the reactive power flow from B to A. Under post-contingency conditions, one of the lines has been disconnected. The generators are still maintaining the voltages at both buses at 1 per unit, but have to provide a lot more megavars to achieve that. So generator at A provides 40 megavars and generator at B provides 67 megavars. Because we have only one line, the current in this line has increased significantly, and therefore the losses are now 15 megawatts. System operators will also need to provide two other types of ancillary services. The first one is stability services, and that can involve things like interstrip schemes that will disconnect generators following the occurrence of a fault. And another form of a stability service is the installation of power system stabilizers. Generators or generating companies want to be paid for providing these services because they feel that they are providing something to the system as a whole rather than something that benefits just themselves. Another service that system operators need to have is the ability to restart the power system following a blackout or black start restoration capabilities. So they will pay generators who are able to start their generating units independently using either small diesel generators or hydro generators. They will pay them some extra money for being there in case there's a blackout and the system needs to be restarted. So far we have discussed the need for ancillary services, but now we need to talk about obtaining ancillary services. And really this means answering three questions. First, how much ancillary services should be bought? Second, how should these services be obtained? And third, who should pay for these services? Let's take the first question. How much ancillary services should be bought? Well, the system operator purchases these services because it works on behalf of the users of the system. Now, if the system operator does not purchase enough services, it won't be able to ensure the reliability of the system and won't be able to maintain the quality of the supply in terms of frequency and voltage. On the other hand, if the system operator purchases too much services, well, that's nice because it makes its life easy, but then the cost is passed on to the system users who really don't particularly want to pay so much for services that they don't need. So really, the system operator should perform a cost-benefit analysis to figure out what is the right balance between the value of the services against their costs. The value of the services is measured in terms of how much they improve the reliability and the service quality. The cost is, well, whatever it has to pay the generators and others to provide these services. Now, this cost-benefit analysis is a complicated probabilistic optimization problem. But one way to deal with it would be to give to the system operator a financial incentive to acquire the right amount of services at minimum cost. The next question is, how should these services be obtained? Well, there are really two approaches. One is to make the provision of services compulsory, and the other one is to create a market for ancillary services. Both of these approaches have advantages and disadvantages, and the choice will be influenced by the type of service, the nature of the power system, and also by history. How did we get there? Let's first look at compulsory provision of ancillary services. That's really saying that to be allowed to connect to the system, generators will have to be obliged to meet some conditions. For example, we can say that generators must be equipped with a governor with a 4% droop, and therefore all generators will contribute to frequency control. Or we could say that the generators must be able to operate from 0.85 lead to 0.95 lag. Therefore, all generators will contribute to voltage control and reactive support. Now, compulsory provision has advantages. It represents a minimum deviation from traditional practices in vertically integrated utilities. And it's also very simple. You just write the rules and you tell the generators that they have to follow them. And it will usually ensure that the system operation reliability and quality of supply will be met. The disadvantage of compulsory provision is that it's not necessarily good economic policy. You may provide this way more resources than you need and cause unnecessary investments. Not all generators need to help control frequency, and not all the generating units need to be equipped with a stabilizer. It also discourages technological innovation because the definitions are probably going to be based on what the generators usually provide. And some generators may have to provide a costly service for free. For example, generators will complain that providing reactive power increases losses and reduces the active power generation capacity of their generating units. There are other disadvantages. For example, there's a problem with equity. How do we deal with generators that simply cannot provide some services? For example, nuclear units are not particularly good at frequency response and probably shouldn't be asked to contribute to frequency response. And there are also issues of economic efficiency. It's not a good idea to force highly efficient units to operate part loaded to provide reserve. And it's usually more efficient to determine centrally how much reserve is needed and commit additional units to meet this reserve requirement. Conclusion is that compulsory provision of ancillary services is not going to be applicable to all services. So it is probably better to try to put in place some kind of market-based scheme for the provision of ancillary services. So how could such a market for ancillary services work? Well, once again, one size does not fit all, and we're probably going to need different market arrangements for different services. We could have some long-term contracts, and this would work for services where the quantity need does not change and the availability depends on equipment characteristics. For example, black start capability, inter-trip schemes, power system stabilizers, and frequency regulations are all types of ancillary services that probably should be dealt with using long-term contracts. On the other hand, for other services are probably dealt in a reasonable manner using a kind of spot market. And those would be the services where the needs change over the course of a day and where the price of the service or the cost of the services is probably going to change because of the interactions with the energy market. So for example, services are probably traded or should probably be traded on a spot market linked to the energy market. In general, the system operator is probably going to want to reduce its risk by using a combination of spot markets and long-term contracts to provide these services. So what are the advantages of having markets for ancillary services? Well, it's going to be a bit more economically than compulsory provision because the system operator is only going to buy the amount of service that it needs, and only the participants that find it profitable to provide such services will take part. A market also helps determine the true cost of the service if it is a sufficiently competitive electricity market. And also, having a market is going to open up opportunities for innovative solutions. We are not stuck in defining compulsory services the way they have always been provided before, without looking at possibly new ways of achieving the same thing at a lower cost. Markets for ancillary services also have some disadvantages. It's going to be a bit more complex, and it's probably not applicable to all types of services. And we're also going to have to deal with the potential for abuse of market power. As I mentioned earlier, reactive support has a strong local component, and therefore reactive support in remote parts of the work is highly susceptible to the abuse of market power. Therefore, markets for reactive power will need to be carefully regulated. It is clear that there are interactions between the provision of reserve and the production of energy. That's why in centralized markets we have what's called co-optimization of energy and reserve. So let's look at these interactions in some more detail. If a generator provides reserve, that means that there is a limit on how much energy it can produce. And if this generator provides reserve, well, maybe some more expensive generators will have to produce the energy that our first generator might have produced. And these partly loaded generators that provide reserve may then end up operating less efficiently and may need compensation for the fact that they're providing reserve rather than providing electricity. So centralized electricity markets need simultaneous clearing of the energy and reserve markets, just to make sure that no participant is disadvantaged and also to make sure that the overall system is optimized. Let's explore this with a simple 4-unit system. Let's suppose that these 4 generating units have a constant marginal cost, and the table shows these marginal costs. It also shows the maximum power output of each of these units. And units 1 and 4 cannot provide reserve, maybe because they are very large inflexible generating units such as nuclear units, and therefore do not have the ramping capability needed to provide reserve. On the other hand, units 2 and 3 can provide some reserve, and the amount of reserve that they might be able to provide are shown in the table. Now, for the sake of simplicity, we will ignore the minimum power output of the generators and the startup costs. Now, Unit 2 and Unit 3 have declared that they can provide a certain amount of reserve, 160 megawatts for Unit 2 and 190 megawatts for Unit 3. That may be determined by their ramping abilities. But there are also limitations on how much Unit 2 and Unit 3 can provide in terms of reserve because of how much energy they can produce. Up to 70 megawatts of energy production, Unit 2 can provide its 160 megawatts of reserve capacity because its maximum capacity is 230 megawatts. But if Unit 2 provides more than 70 megawatts of energy, the amount of reserve it can provide decreases and reaches zero when it's at its maximum power output of 230 megawatts. Similarly, Unit 3 can provide 190 megawatts of reserve capacity up to 50 megawatts of energy production, and then this decreases linearly up to 240 megawatts of energy production, at which point Unit 3 is no longer able to provide any reserve. We will make a few more assumptions about this market. First, we will assume that it is perfectly competitive, so we don't have to consider market power abuse. We will also consider that generators submit bids for energy only. We will relax this constraint a bit later. And we will assume that the market operator or system operator dispatches generation to meet the load at minimum cost while providing the reserve needed. Now, this reserve requirement is assumed to be constant and equal to 250 megawatts, and we will consider how this can be done as the load varies between a minimum of 300 megawatts and a maximum of 720 megawatts. We can formulate this co-optimization problem as an optimization problem where our decision variables are the power produced by each of the generators, P1, P2, P3, P4, and the reserve provided by each of these generators, R1, R2, R3, and R4. Our objective is to minimize the overall cost of producing energy. So the marginal cost of generator 1 times P1 plus the marginal cost of generator 2 times P2, and so on. And then we have to consider the constraints. The first constraint is on the load generation balance. P1 plus P2 plus P3 plus P4 must be equal to the demand. And we have the minimum reserve requirement, saying that R1 plus R2 plus R3 plus R4 must be greater or equal than our reserve requirement, which we have set at 250. And then we have the minimum and maximum output of the generators, which vary from a minimum of 0 to various maxima as shown on the slide. Now we also need to consider the limits on the reserve capabilities of generating units, which may be determined by their ramp rate. So in this example, we'll assume that generator 1 is not able to produce any reserve. Generator 2 can produce between 0 and 160 megawatts of reserve. Generator 3 can produce between 0 and 190 megawatts of reserve. And our generator 4 is not able to produce any reserve. And then we have to consider that a generator produces either energy or reserve, but that the total cannot exceed its maximum output. So P1 plus R1 must be less than 250 megawatts, which is Pmax for generator 1. P2 plus R2 is less than 230 megawatts, which is the maximum output of generator 2, and so on. So how can we solve this problem? Well, we can observe that all the objective functions and all the constraints in this problem are linear, so we can formulate it as a linear programming problem and use one of the available linear programming solution engines. And if we run this problem for various values of load, we do get the table shown on this slide. Now that's the solution. We can also look at the Lagrange multipliers associated with the constraints, as they are provided by the linear programming engine. And in particular, the load generation balance, Lagrange multiplier associated with the load generation balance constraint is going to give us the price of energy, while the Lagrange multiplier associated with the reserve requirement constraint will give us the price of reserve. However, just putting this in a linear programming engine doesn't give us much information. So to get a better feeling for what's going on, we will try a solution by hand of this problem. And in this particular case, this can be done reasonably easily, and we can use it to really get a feeling for what's going on. We'll start by observing that unit 1 is the cheapest and will therefore always produce its maximum output because its marginal cost of energy is so much cheaper than the others. Now we also notice that both unit 2 and 3 are needed for reserve, so we must have R2 plus R3 greater or equal to 250, but at the same time R2 cannot be greater than 160 and R3 cannot be greater than 190. That means that R3 will have to be greater or equal to 90, and therefore the amount of energy that generator 3 can produce will have to be between 0 and 150. And similarly, because R3 has to be less or equal to 190, R2 is going to have to be greater or equal to 60, and therefore P2, the amount of energy produced by generator 2, is going to have to be between 0 and 170. Let's first consider what happens when the demand is in the range from 300 megawatts to 420 megawatts. Well, unit 1, as I mentioned earlier, is by far our cheapest unit, so it will produce its maximum output of 250 megawatts. Unit 2 is our next cheapest generating unit, and it's going to be the marginal unit because we will only need unit 2 to produce energy on top of unit 1. So as the demand increases from 300 to 420 megawatts, the production of unit 2 will increase from 50 to 170 megawatts. And it will set the marginal price of energy, because it is the marginal unit, at its marginal cost of energy, which is $17 per megawatt hours. In terms of reserve, well, having unit 2 and unit 3 in the system, we have in this range of load, we have more than enough reserve with unit 2 and unit 3. Therefore, the price of reserve in this range is equal to 0. When the load reaches 420 megawatts, we reach a point where something is going to have to change, because unit 2 cannot produce more than 170 megawatts of energy, because as we have seen before, it must provide 60 megawatts of reserve. At that point, therefore, we need to start producing energy with unit 3, which becomes the marginal unit. And the production of unit 3 is therefore going to start increasing from 0, and we'll see that will be for up to 50 megawatts. Therefore, the marginal price for energy becomes the marginal cost of energy as produced by unit 3, which is $20 per megawatt hour. But what about the price of reserve? Well, because we assume a perfectly competitive market, the price of reserve is going to be the marginal cost of an additional megawatt of reserve beyond the 250 megawatts that we normally require. But in this case, unit 3 is already providing its maximum reserve of 190 megawatts. That's the maximum reserve that it can provide because of ramp rate limitation. So to get one more megawatt of reserve, we would have to provide it from unit 2. But that means we need to reduce the energy output of unit 2 by 1 megawatt and increase the output of unit 3 in terms of energy by 1 megawatt. Therefore, the price of reserve is the cost of this switch meaning it's 20 minus 17, that's $3 per megawatt hour. That is the difference in the marginal cost of producing energy with Unit 3 and Unit 2. When the load reaches 470 megawatts, Unit 3 reaches a production of energy of 50 megawatts, which is the maximum that it can produce if it still is going to provide 190 megawatts of reserve. Therefore, at that point, Unit 4 becomes a marginal unit, and its production is going to start increasing from 0 to 250 megawatts, which is its maximum output. And therefore, the price of energy in that range will be the marginal cost of energy produced by Unit 4, which is $28 per megawatt hour. Now, the reserve constraints going to limit the production of Units 2 and 3 at 170 megawatts and 50 megawatt respectively. So if we want to get 1 more megawatt of reserve, we need to reduce the output of Unit 2 by 1 megawatt, increase the output of Unit 4 by 1 megawatt, and therefore the price of reserve is the difference between the cost of production of energy with Unit 4, 28, and with Unit 2, 17. It's therefore $11 per megawatt hour. So the graph on this slide summarizes what we have discussed, and you can see the various transitions that take place. We start with a reserve price of 0, and then it gradually increases, and we start with an energy price at 17, and at each of these transitions it's up. Let's explore whether these units make a profit from providing this reserve. And again, we need to look at these different load ranges separately. So starting with the range between 300 and 420 megawatts, we notice that in that range, Unit 2 was the marginal unit for energy. It was therefore not making a profit on the sale of energy. And during that range, the price of reserve was 0. It was also therefore not making any profit on the provision of reserve. Moving on to the range between 420 megawatts and 720 megawatts. Well, we saw that in that range, the output of Unit 2 was capped by the reserve requirement, and that Unit 3 was the marginal unit in terms of production of energy. The energy price was $20 per megawatt hour, and the reserve price was $3 per megawatt hour. The marginal cost of Unit 2 is $17 per megawatt hour. Therefore, Unit 2 gets opportunity cost for every megawatt of reserve that it provides, and it is thus not penalized for providing reserve rather than energy. Finally, let's look at the range of load between 470 and 720 megawatts. In this range, Unit 4 is a marginal unit, and the energy price is therefore $28 per megawatt hour. So Unit 2 makes a profit of $11 per megawatt hour for its energy production. And because the reserve price is also $11 per megawatt hour, well, the revenue from the reserve is equal to the opportunity cost of Unit 2. Therefore, Unit 2 is indifferent to producing a reserve. On the other hand, it's kind of interesting to note that Unit 3 makes a profit on energy and on reserve because it is marginal for neither providing reserve nor energy. The graph on this slide shows what happens to the profitability of Unit 2 as the load changes. We can see again that up to 420 megawatts, Unit 2 is marginal and the price of reserve is 0, therefore it doesn't make a profit. At 420 megawatts, it starts making a profit from the sale of energy, and at 470 megawatts, it starts making a profit on the sale of reserve. So the previous example shows that co-optimization ensures that units will not be disadvantaged by the fact that they have to provide reserve. But some markets are allow generators to bid separately for energy and reserve. And the idea being that these bids for reserve may reflect the loss of efficiency or additional maintenance requirements that these units may face if they provide reserve. So let's suppose, take another example, that in addition to the marginal cost of energy, these units also provide the marginal cost of reserve. And in this case, we'll assume that units 1 and 2 assume that they have a marginal cost of reserve of 0. Doesn't make much difference for unit 1 because it doesn't provide reserve anyway, while units 3 and 4 provide a marginal cost of reserve of 5 and 7 respectively. Therefore, the objective function or changes where we now not only are trying to minimize the cost of providing energy, but also the cost of providing reserve on these bids, which are themselves supposed to be bid on the marginal cost of reserve. Now, if we put all of this into a linear optimization engine, we get the following results. And it's a bit long and tedious, so I'm not going to go through the details. If you're interested, there's a very good discussion in the textbook by Kirschen and Strabats. The point is that co-optimization is going to achieve a cost minimization and a fair treatment of the generators, and also is going to make sure that we have the amount of reserve that has been specified. I would like to discuss briefly now the provision of ancillary services from the demand side. Now, in a truly competitive environment, really the system operator should not make any donation in favor of any type of participant, whether they are from the supply side, the generators, or the demand side, the consumers. And therefore, creating a market for ancillary services opens up an opportunity for the demand side to participate and provide ancillary services. Now, that would be great, but unfortunately the definition of ancillary services are still very much based on traditional practices. It would be nice if that could change. So, what is providing ancillary services from the demand side? Well, you would increase the number of participants who can provide these services. Therefore, you would increase the competition and lower the costs. It would also make possible better utilization of the resources. For example, it's better to provide reserve with interruptible loads rather than partly loaded thermal generating units. And that's particularly important because the proportion of generation that comes from new energy sources is going to increase, and therefore we may need more reserve. And contrary to common wisdom, the demand side may be a more reliable provider of ancillary services, of reserve in particular, because you are relying on a large number of small providers rather than a small number of large providers. And if one of the small number of large providers fails, well, you have a large deficit. Now, what are the opportunities for the demand side to provide ancillary services? Well, the demand side could provide different types of reserves in the form of interruptible loads. It might also be able to contribute to frequency regulation, particularly if you have power electronics-based variable speed pumping loads, where you could make the load reacting to the frequency. Let's now consider the question of who should pay for ancillary services. And let's start with the observation that not all users value reliability and quality of supply in the same manner. For example, the value of electricity to consumers is at least 2 orders of magnitude of the benefit that it provides to producers. And if you have an unreliable or poor quality electricity supply, well, the damage it can make to a semiconductor manufacturing facility are much larger than what you would do to an irrigation load, which is briefly interrupted and then you resume pumping. So in an ideal world, the user who value reliability more should get more reliability and should pay for it. Unfortunately, with the current state of technology, this is not possible. and therefore the system operator provides an average level of reliability to all users. And the cost of these and the ancillary services that are required to provide this reliability is shared by all users on the basis of their consumption. Now, sharing the cost of ancillary services based on the amount of energy consumed is not economically efficient, because some participants in the electricity market increase the need for services that more than others. And therefore, these participants should be made to pay a larger share of this cost to encourage them to change their behavior. And for example, let's talk about allocating the cost of reserve. Now, reserve is provided to prevent the collapse of the system when there's a large imbalance between load and generation. And these large imbalances usually occur because of the failure of a generating unit. So it would make sense to say that the owners of large generating units that fail frequently should pay a larger proportion of the cost of reserve, because that would encourage them to improve the reliability of their units. And in the long term, that would reduce the need for reserve and reduce the overall cost that everybody ends up paying for reserve. Let's change perspective and let's now consider the business of selling ancillary services. Now, ancillary services represent another business opportunity for generators. However, the amount of ancillary services that they can sell is limited for two reasons. One, there are the tech characteristics of their generating units, for example, maximum ramp rate in terms of selling reserve and frequency regulation, or the reactive capability curve when doing voltage control or reactive support. There's also an issue of opportunity cost, because if you sell reserve, for example, you can't sell as much energy. So from the perspective of a generator, if it wants to sell reserve, it needs to jointly optimize the sale of energy reserve. So let's explore this using a simple example where a generator tries to find out how it could sell both energy and reserve. And this generator is going to try to maximize the profit that it makes from the sale of energy and reserve. But to keep things simple, we're going to make a number of assumptions. First, we'll consider there is only one type of reserve service that this generator can sell. Second, we'll assume that the markets for energy and reserve are perfectly competitive. That means that the generator is a price taker in both markets and that it can sell any quantity that it decides on either market. Now we'll consider one generating unit over 1 hour, so we don't have to worry about startup costs, minimum uptime, minimum downtime, and other scheduling constraints. And finally, we'll assume that there are no special payments made if this reserve is exercised. So we're just talking about payments, revenues, and profits from providing the reserve. The first thing that we need to do is define the notations that we're going to use. So we will call pi 1 the market price for energy in dollars per megawatt hour. Pi 2 will be the market price for reserve, which is dollar per megawatt per hour, which, strictly speaking, is the same thing as dollar per megawatt hour, but I write it this way to emphasize the difference. X1 will be the quantity of energy that is bid and sold, because we assume that this generator can sell anything it decides to bid. And X2 will be the quantity of reserve that is bid and sold. Pmin is the minimum power output of the generator. Pmax is the maximum power output of this unit. Rmax is the upper limit on the reserve, for typically would be the ramp rate times the delivery time for this particular reserve product. C1 of x1 is the cost curve of producing energy, so this is a classical cost function that we have seen before. And C2 of x2 is a cost of providing reserve. Now, this is an actual cost, this is not an opportunity cost. So we can formulate this problem as an optimization problem. The objective is to maximize the profit, so it's a function of the quantity of energy x1, the quantity of reserve x2 that are provided by this generator. The revenue is pi1 x1 for energy plus pi2 x for reserve minus c1 x1, the cost of producing energy, minus c2 of x2, which is the cost of providing reserve. We also have constraints. First, that the quantity of energy plus the quantity of reserve must be less or equal than the maximum output of the generating unit. Second, that the amount of energy must be greater or equal than the minimum output of this generating unit. And that the amount of reserve x2 must be less than the maximum reserve that can be provided by a unit. Remember, that has to do with the ramp rate. And we will assume that this ramp rate constraint is significant in the sense that it's less than the difference between Pmax and Pmin, which means that the unit cannot ramp up from its minimum to its maximum in less time than it has to provide or to deliver this reserve. So putting the objective function and the constraints together, we get a Lagrangian function of the two decision variables x1 and x2, and we have three Lagrange multipliers, mu1, mu2, and mu3, one for each of these constraints. Mu1 relates to the maximum output of the generating unit, mu2 to the minimum output, and mu3 to the ramp rate constraint on the reserve. The next step is to write the optimality conditions for this problem. We have 5 optimality conditions because we have 5 variables. The first two equations correspond to the partial derivatives of the Lagrange with respect to the decision variables x1 and x2. And the last 3 correspond to the partial derivatives of the Lagrangian with respect to the Lagrange multipliers mu1, mu2, and mu3, and those simply give us the inequality constraints. Now, because we have inequality constraints, we also must have the complementary slackness conditions, essentially say that these inequality constraints are or are not binding. We'll consider various cases based on which constraints are binding. So we do that by setting the Lagrange multipliers equal to 0 or not 0. So the first case, we assume that all the mu's are equal to 0, which means that there are no binding constraints. So if I take the first optimality conditions and set mu1 equals 0, mu2 equals 0, I get dc1 over dx1 equals pi1. And if I do the same thing in the second optimality condition, I get dc2 over dx2 equals pi2. So this actually tells me that we should provide energy and reserve up to the point where the marginal cost of providing energy and reserve is equal to respectively the price of energy and the price of reserve. So in this case, we provide both, and there are no interactions between the provision of energy and the provision of reserve. Second case that we will consider is a case where mu1 is positive and mu2 and mu3 are both 0. Well, mu is the Lagrange multiplier that corresponds to the constraint on the total generation capacity. Essentially, it says that x1 plus x2 must be equal to Pmax. Therefore, the generation capacity is fully utilized either to produce energy or to provide reserve. If we use these information about mu1, mu2, and mu3 in the optimality conditions, we get to the conclusion that pi1 minus dc1 over dx1 must be equal to pi2 minus dc2 over dx2 must be equal to mu1, which is, because of the complementary slackness position, positive. Pi1 minus dc1 over dx1 is the profit that I make on the selling energy, and pi2 minus dc2 over dx2 is the profit that I make on selling reserve. Therefore, this expresses the fact that the marginal profit on reserve should be equal to the marginal profit on energy. In a way, what this tells us is that we should divide the production of they should divide our generation capacity in such a way that the profit on reserve is equal to the profit on energy and fully utilize this generation capacity. The next case has mu1 equals 0, mu2 positive, and mu3 equals 0. Now, mu2 corresponds to the claim that the x1 equals p min, therefore unit operates at its minimum stable generation. If we put those values of the Lagrange multipliers in the optimality condition, we get the following. The first one gives us that dc1 over dx1 minus pi1 equals mu2. The second one gives us that dc2 over dx2 equals pi2. Therefore, on these conditions, this generator makes a marginal profit on the reserve. There is a loss on the energy because the cost of producing energy, marginal cost of producing energy, is higher than the price at which this energy is being sold, and this is minimized by operating the generator at its minimum stable generation. Now, all of this happens because the KKT conditions guarantee only marginal profitability, not an actual profit. Cases 4 and 5 correspond respectively to mu1 and mu2 positive and mu3 equals 0, and to all three Lagrange multipliers being positive. Now, these cases are not interesting because we have assumed that the ramp rate limit is then the difference between the maximum and minimum output of a generator. In case number 6, mu1 and mu2 are both 0, and mu3 is positive. This means that the reserve is limited by the ramp rate, or x2 is less or equal than R max. Put those values of the Lagrange multipliers in the first optimality condition, we get that dc1 over dx1 equals pi1. And into the second optimality condition, we get that pi2 minus dc2 over dx2 equals mu3, which is positive. So the first one shows us that we are maximizing our profit on energy, meaning we're choosing x1 in the way that maximizes that profit. And we are also making a profit on the reserve, but this profit could be increased if the ramp rate constraint could be relaxed. Case number 7, mu1 and mu3 are positive and mu2 is equal to 0. This means that we have two binding inequality constraints. First, the maximum capacity constraint, x1 plus x2 equals P max, and then the ramp rate constraint or limit on the availability of reserve, x2 equals R max. Now note that putting these two constraints together, we can find that x1 is max minus R max. Going to the optimality conditions, if we insert mu2 equals 0 in the first one, we get that I1 minus dc1 over x1 equals mu1. Therefore, there's going to be a profit on the sale of energy. And the second one, we get pi2 minus dc2 over dx2 equals mu1 plus mu3 is positive. Therefore, there's going to be also a profit on reserve. So in this case, the sale of energy and the sale of reserve are both profitable. The sale of is more profitable because it's mu1 plus mu3, which is a difference between the price and the marginal cost, but the amount of reserve that can be sold is limited by the ramp rate constraint. In the final case, mu1 is equal to 0, and mu2, mu3 are both positive. That means that we again have two binding inequality constraints, the minimum output constraints and the reserve limits constraints. So we have x1 equals p min and x2 equals r max. In this case, the optimality conditions tell us that pi 1 minus dc1 over dx1 equals minus mu2 is negative, so there is a loss on the sale of energy. And the second optimality constraint tells us that pi 2 minus dc2 over dx2 equals mu3, which is positive. So the sale of reserve is profitable, but limited by the ramp rate constraints. The sale of energy is unprofitable, and if we want to find out if the overall this generator is going to make a profit, well, we would need to plug in the numbers and calculate the actual values and not just the marginal profitability.